Okay, good morning, welcome back. Now, what I want to look at this morning is to look at, I'm going to continue with bonding, earth bonding, and this is going to be and earth and bonding. Hmm, 1 second. Bear with me for a moment, let me just check something here. I don't want to be calling something the same name as it, because it's important that you recognize which is which. Right, let me just recap that. Okay. Yeah, once again, I'm just looking at something here. Earthing and bonding to be able to give example of each. Found it, thank you. Okay. Right, earthing and bonding 2. Okay. Yeah, sorry about that. It's going to be earthing and bonding 2. Okay, I'm just get to between that, more space between it. Okay, thank you. Earthing and bonding 2. Let's. I've done earthing and bonding 1. This will be session 5, earthing and bonding 2. Okay. And here we're looking at aims and objectives of this session to be able to differentiate between terms earthing and bonding, to be able to list possible explored and extraneous conductive parts. Similar aims and objectives as before, because it is a continuation of earthing and bonding. Okay. Right. Okay. Let me get to work. Okay. I hope you will find this useful. Okay. And give it me while I get set up. Okay. That's good. Okay, let me get to work. Thank you. And I can go into this. 1 second. Come on. Okay. I don't want that started yet. No, I don't do that. Good. Okay, good. I can think I am in business, yes. Okay, let's run with this now. Okay, earthing and bonding 2. Okay, it's a continuation from earthing and bonding previously. Okay. Mentioned the objectives and aim objectives before. Don't need to do it again. Look at the revision part, which you've covered already. Okay. To make sure you understand that. Okay. The earthing and bonding. Earthing in a mains AC power electrical system is a conductor that exists primarily to help protect against faults, and which in normal operation does not carry current. Bonding involves joining together metalwork that is or may be earthed, so that it is at the same potential, i.e. voltage, everywhere. Okay? And you're looking for zero voltage in regards to bonding. Okay? Earthing of a small domestic installation. Now, the conductor from the supply intakes is called the earthing conductor, and everything else is a bonding conductor. Okay. And here you have a set out of your gas incoming supply, your bonding cables where they are. Okay. Have you met? Okay. You have your incoming mains, water. Yeah, and you have your connected to your gas supply. Okay. Just make sure we can pan back. Pan now. Get everything into to view. Okay. Now I found this one quite useful because I've had this video now for some time, since approximately 2008, and because you deal with so many videos, you probably don't get around to seeing them all. Earthing and bonding conductors. Now BS7671 defines an earthing conductor as a protective conductor connecting the main earthing terminal of an installation to the earth electrode or other means of earthing. BS7671 defines a bonding conductor as a protective conductor providing equipotential bonding. Now make sure that is still the case and that the earthing and definition given here is up to date. But I don't believe it changed much. Now again, it is your responsibility to ensure that you've checked with the BS7671, the 18th or the 17th edition of the IE regs, or in your case, some of your cases could be the 19th edition of the IE regulations. Make sure you're familiar with that, and that is your job to ensure that you are compliant. Earth electrodes. Now, when the supply authority has not provided an earth electrode, and we have to provide earth to an installation, it will be in the form of an earth electrode. Now, again, be familiar with which systems you will need to put an earth electrode. And normally, if I remember correctly, it's normally a TT system, but don't hold me to that. It is check for yourselves. Find out, make sure you know, okay? BS761 allows for a variety of earth electrodes, earth rods or pipes, earth tapes or wires, earth plates, underground structural metal work embedded in foundations, welded metal reinforced of concrete embedded in the earth, not pre-stressed, lead sheets or other coverings of cables in accordance with current regs, other suitable underground metalwork, etc., etc., etc. Okay. Now, again, it is your responsibility to ensure you're compliant with BS7671, either the 18th or 19th edition. Basically, my regs was the 17th edition. That was my last regulations. Okay, and I have the cover books here to show you. And here we're looking at an earth rod. Okay, we're just going to make sure that we can get this fully. Okay, earth rod. Now, this is the most common type of earth electrode. It is made of copper or copper-clad steel. The connection to the electrode must be accessible so that tests can be carried out on it. Any earth electrode you install must be at least 9 meters away from any supply authority's electrode or cable sheath. Now again, check to ensure that the current regulation is still standing at 9 meters or whether it now needs to be further away. Okay, that's your responsibility to check and check again. The connection of the earth conductor to the earth electrode must have a warning notice attached to it. And you all know the warning notices that is required. So make sure you are compliant with that as well. Okay. Connection of an earth rod. Okay. Now this earth electrode is accessible via an inspection cover. The connection of the earth conductor and the earth electrode must have a warning notice attached to it. Okay. Now you see this one here is set in the ground and coming underneath the general mass of earth and into the property. The interesting thing here is that they're using pipe. Now, what kind of pipe would you think they would need to use in order to insert it in the general mass of earth? Black enamel, galvanized, which pipe would give you the longer life? And it can't be plastic because plastic could rupture if somebody stuck a fork in the ground. So you will need to be very careful here. Okay, so it does have to be metal. Okay, it is essential that you understand that. Okay, and again, check with the regulations that you are compliant. Okay, other types of electrodes. There are other types of electrodes, parallel connection strips or copper tape. Okay, in rocky soil, copper tape, stranded conductors, or wire mesh can be used. Care must be taken when burying the electrode to prevent damage by disturbance. Okay, it depends on where you are. Okay, so you have a variety of variations of types here. You got parallel connection strips of copper tape. You got a plate. You have a lattice copper tape. You have radial connected strips of copper tape, etc. Okay. But make sure that you look at what is required for today in regards to the environmental impact as well. So very well looking at the environmental impact, but the problem is the cost, isn't it? Connecting earth conductors to earth electrodes. Connecting earth conductors to earth electrodes can be done by, you can braze it. That means kind of welding, but brazing, okay, with the acetylene torch, etc. Please be sure that you do not go using acetylene torches without supervision. Tape connectors, mechanical clamping devices, special welding techniques. When a joint is made, care should be taken to ensure the joint is protected. It should be coated with grease or bitumistic paint. Now, why do you think it needs to be lubricated with grease? Because grease does not rust, and grease prevents water ingress and prevents the welding coming away from the welded plate, thereby making the earth ineffective and causing a quite possible lethal potential of shock. So that is why you're looking at making sure that you use plenty of grease and or bitumistic paint. Okay. Now Faraday's cage. Now it's interesting that I've had this video here for a while, but I've never taken the time to study it because you know when you're going to the next class and the next class that you don't really get time to do certain things. But I'm looking at Faraday's cage here. Michael Faraday stood in a metal cage insulated from the floor. He then charged the cage to a large voltage. He did not receive a shock as he was at the same voltage potential as the cage. This is the principle of an equipotential zone. Because everything is at the same potential, you will not get a shock. But it's interesting, had Faraday put his hand or stuck his finger out through the cage and touched any metalwork external to the cage, I'm sure he would have received quite a shock. But again, that could be my misinterpretation. So take no notice of me. I'm just making an assumption. Now here we have a little note. A teacher has come up with the idea to curb the cheating epidemic via text messages using mobile phones in the country by lining every exam room with a Faraday light cage. It would be probably an idea, but people shouldn't have their mobile phones in class anyway, in exams at any point in time. That's common sense. Okay. Now here we have the equipotential zone, and you're looking here at the bath, the wash basin, the latrine, okay, airing cupboard, shower cubicle, etc. Okay, and it's showing you those components that should be earth and where. Now you need to be sure again that you are compliant with current regulations, and that is the current IEE regulations in respect of electrical installation work. Okay, I cannot emphasize that enough. The bathroom has become an equipotential zone within an equipotential zone. The pipes, radiators, etc. have been bonded to ensure that all metalwork remains at the same voltage should a fault occur. Okay. In short term, should a fault occur in the bathroom due to an electrical fault or the shower unit, then that shower unit fault should be able to draw enough current to trip the protective device that will protect the individual in that bathroom or shower. Okay. Now, my beef at the moment is, let me show you what I was thinking of. Well, I can't show you, but when you look at the video, you'll see what I'm talking about. Um, 1 second. A second. It was to do with the fuse rating when the protective current went. Did I get that? Anyway, it was to do with the rating of the fuse. It was to do with the rating of the fuse, right? Now, what I have a problem with is that the circuit breaker is designed to trip at 30 milliamps. The RCD also is designed to trip at 30 milliamps. Now, it's okay, for the scene is okay. Now, if the RCD is set to trip at 30 milliamps, it means that, and the RCD is also set to trip at 30 milliamps, doesn't that mean that when a fault develops, that the first thing that's going to go will be the RCD? Now, technically speaking, you would think that the circuit breaker should operate first, but because the circuit breaker and the RCD is rated at the same milliamps to operate at, the RCD operates quicker than the circuit breaker, which it is meant to do. But shouldn't we be looking at the possibility that the circuit breaker should be operating at 25 milliamps rather than 30 milliamps? Thereby, if the circuit breaker is defective, then the RCD comes into play to ensure as the backup to protect the circuit should be no out. But at the moment, you have a bank of RCDs. Sorry, let me rephrase that. You have a bank of Circuit breakers controlled by an RCD, which when a fault develops at this point in time, the RCD trips out. Now I've got it in my own house. Okay, the circuit breaker trips out, the RCD trips out, and it knocks out 5 of the circuits approximately. So why isn't the circuit breakers calibrated to trip at 25 milliamps and the RCD becomes the backup to that if the circuit breakers become defective? But it's just my little beef, okay? Um, that's the thing that I noticed here. I was trying to look for it because it triggered my mind just now, and but I can't. Okay, right. Coming up to our last slide. I'm going to have to recap this actually because I must admit I got a little bit carried away. Well, outside increased potential zone, and here we're looking at at an internal wall, and we got a lawnmower outside. Okay, and here, yes, this is probably what I was looking for. This socket must be protected by an RCD having a maximum tripping count of 30 milliamps. So the RCD will trip at 30 milliamps, but the circuit breaker will also trip at 30 milliamps. Now, I might be wrong. It's possible, could be incorrectly wrong, but I'm just thinking of my time before. So I apologize if I'm incorrect. Okay, but from what I can gather, that the circuit breakers are designed to trip at 30 milliamps, and here we have our RCD tripping at 30 milliamps, and the RCD will trip before the circuit breaker, and that is what I'm saying basically. Okay, the circuit breaker should be tripping before the RCD. The RCD becomes your final backup, not tripping before the circuit breaker. But that's just my bugbear. I apologize if I'm looking at it from a different way, and I might be totally incorrect. So I apologize if that is the case now and then. Okay. Okay. That will be it. Let me just go back and check through each one. Okay. I have to do that because I was blabbering on. Okay. I just need to make sure that they're all in frame. Okay. Wait a second. I'm just reducing the talking at the moment so I can make sure I get all this in view. Okay. 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 Yeah, 1 second. Yeah, I can see everything. Yeah. Okay. Okay, just with me. Okay. Yeah. Okay, thank you. Hope you found this useful. Bye bye.